You ever wonder how a scientist actually goes from a simple, I wonder if, to a really confident, data-backed conclusion? How do we take these vague questions about the world and turn them into hard-hitting, credible answers? Well, it's not magic. It's a powerful, systematic process. So let's dive into this journey from hunches to hard science. This quote right here, this is the heart of our entire explainer. It's a kind of radical idea when you first hear it. The best science isn't about proving yourself right. It's about having the guts to try and prove yourself wrong. A theory that can't be challenged, one that you can't put in mortal danger with a tough experiment, well, it isn't really a scientific theory at all. It's more like an article of faith. So how do we put our theories in mortal danger? Well, back in the 1960s, a physicist named John R. Platt noticed something. Some fields of science were just leaping forward, making huge progress, while others were just kind of trudging along. He argued it wasn't about having more money or smarter people. It was about a specific, systematic way of thinking that he called strong inference. Now, you might be thinking, hey, that sounds like the scientific method from middle school. And you're not wrong, but this is like a supercharged version. It's not just about having one hypothesis and testing it. No, it's about coming up with a whole family of competing ideas and then systematically and ruthlessly trying to kill them off with clever experiments until only the strongest one is left standing. Platt had this great analogy for it. He said it's like climbing a logical tree. At every fork in a branch, you have your different hypotheses. A really well-designed experiment acts like a signpost. It forces you to pick a path by proving the other one is a dead end. And you just keep doing that, branch by branch, climbing higher and getting closer to the truth by systematically ruling out everything that isn't true. Okay, so that's the big idea, the philosophy. But what does it actually look like in practice? How do scientists really walk this path from a simple question to a solid conclusion? Well, it turns out there's a blueprint for that. And this diagram just illustrates that blueprint perfectly. You see, you start with some big ecological question. That question forces you to come up with testable hypotheses and make some predictions. Then you've got to design a study. Get your hands dirty and collect some data. And that data eventually leads you to statistical analysis. And that's the crucial step where you can finally draw an inference, circling all the way back to answer your original question. But once you've collected all that data, you're not done. Not even close. You're basically holding a pile of raw numbers. And honestly, raw numbers don't really tell you much on their own. To make any sense of it all, to find the pattern hidden in the noise, you're going to need the right tools. And welcome to the world of descriptive statistics. Think of these as the fundamental tools in a data scientist's toolkit. The hammers, the wrenches, the screwdrivers. They're what allow us to take a big, complex, messy data set and boil it down into just a few numbers that actually mean something. So this toolkit, it really has two main jobs. The first one is to find the center of your data. What's a typical value? We call this central tendency, and you've definitely heard of these. The mean, which is just the average, and the median, which is the value smack dab in the middle. The second job is to measure dispersion, or how spread out everything is. Are your data points all clustered together, or are they scattered all over the place? That's what something like standard deviation tells us. Now, this slide shows why both of those tools are absolutely crucial. Just knowing the average isn't enough. I mean, look at these two graphs. They could have the exact same average, but their stories are completely different. The skewed data on the left is all piled up on one side with this long tail stretching out. And the bimodal data on the right, it has two separate peaks, which suggests there might be two totally different groups mixed into our data. The shape of the data tells a story that the average alone just completely misses. So we're getting good at describing the data we actually collected, our sample. But here's the million-dollar question. Scientists almost never measure every single thing. They take a sample. So how can they possibly use that small, limited sample to make a confident statement about the whole group, the entire population they're studying? That leap, going from the little bit we know to the vastness we don't, that is the art and science of statistical inference. It's how we make a highly educated, quantifiable guess about the whole world based on just a tiny piece of it. And here's the key insight that makes inference possible. On this chart, look at all those little X's. Those are individual data points. See how they're scattered all over the map? Now, look at the solid black circles. Those are the averages of small samples taken from that same data. Notice how much more stable they are? They're clustered way more tightly around the true population average, which is that solid line. This is the crucial point. Sample averages are way less wild, and because of that, way more reliable than single observation. And we have a name for that stability we just saw. It's called the standard error. It's a really powerful concept. It basically measures the reliability of our sample mean. A small standard error, like we saw with those circles, tells us that if we went out and took more samples, their averages would probably be very, very close to each other. It gives us confidence that our one sample is a pretty good estimate of the whole population. It's a direct measure of our precision. So then we use that standard error to build what's called a confidence interval. This slide is a simulation of that. Each one of those thin vertical lines represents a confidence interval that was calculated from a different random sample. The dotted line in the middle, that's the true answer we're trying to find. Now look closely. Almost all of those vertical bars cross that true line. And that's exactly what a confidence interval does. It doesn't give us one exact answer. It gives us a range of plausible values where we can be reasonably sure the real answer is hiding. Okay, philosophy, toolkits, confidence intervals, let's bring this all together. Let's see how this powerful way of thinking can be applied to solve a real and what seems like an impossible problem. So here's the challenge. How many whales are in the Pacific Ocean? How many tigers are roaming through a jungle? You can't just line them up and count them one by one, right? The problem seems completely impossible. Or is it? Enter this wonderfully elegant solution called distance sampling. It's a method that uses what we can see to make a really powerful inference about what we can't see. The logic is just brilliant. Observers, they walk or fly in these perfectly straight lines called transects. Every time they spot an animal, they record how far away it is from their path. Now, this whole method rests on one really big assumption. If an animal is right on their line, they will see it 100% of the time. And it relies on one key insight. The farther an animal is from that line, the lower the chance they'll actually spot it. And this is where the intellectual leap happens. By plotting the distances of all the animals they did see, they can create a curve that shows how their ability to spot an animal drops off with distance. This curve is called a detection function, and this mathematical model lets them do something amazing. It allows them to estimate the size of the area they couldn't see effectively, and then calculate how many animals were probably hiding in that area. In short, they use what they saw to count what they missed. And there you have it. We started with Platt's big philosophical idea of strong inference, of rigorously testing competing ideas. We moved to the practical statistical toolkit that you need to make sense of data. And we landed on this clever method that solves a huge real-world problem. From a philosophy, to the tools, to powerful answers about the natural world. So this leads me with a final question for you. This whole framework of framing alternatives, of using samples to make inferences, and modeling what you can see to estimate what you can't, it's incredibly powerful. So what are the uncountable or unseeable problems in your own work or even in your own life that you could start to answer by thinking this way?